this course, d is equals to 1 over 4 pi epsilon naught times the integral of the charge, in this case omega, over the distance vector, times dA. Now dA is going to be equals to, let me write this. Okay, so let's say area of a circle is going to be pi r squared, so dA, small a in this case, will be equals to 2 pi r. So instead of writing dA, we can write 2 pi r. So we're going to rewrite it as, we can take out the omega since it's a constant, and we're going to have omega over 4 pi epsilon naught times the integral of 2 pi r over r, distance vector is going to be equals to what? Well, it's going to be equals to the normal r minus r prime. So the magnitude of r, that's what we're interested in actually, it's going to be equals to the z squared minus, we can actually call it x squared, plus, because they're going to be x squared. So in our case, let's substitute in here, we get z squared, actually no, let's keep it as r, because we want everything to be radius, so r squared. Now why r? Because here we're talking about a circle, not a line. That means that the r will go all the way around. So it's not going to be just in the x direction, but also in the y direction. So we can look at it and use spherical coordinates and just say r, because x squared plus y squared, the square root, is always going to be equals to r. And so instead of writing x squared plus y squared for r, we're just going to write r. So squared plus r squared, the square root of, and then we have the r. Now it goes from 0 to capital R. Let me erase this to a space. So we have equals to, well, 2 pi we can take out because it's a constant. 2 pi omega over 4 pi epsilon naught. Let's get rid of it, of course, immediately before we confuse, so we need 2. Then we have integral of 0 to capital R of small r over c squared plus r squared and the square root of dr. So now let's use z substitution. So we can say that u is equals to z squared plus r squared. So du is equals to 2r dr. So dr is actually equals to du over 2r. So I substitute in here, we have on the outside, we have omega over 2 epsilon naught. And then let's not count the boundaries now because we're integrating in terms of u. We have r on the top, like we said, and then u at the power of 1/2. Then we use, instead of dr, we use du over 2r. Now, as you can see, we can erase the r's, and we can say that it's going to be equals to, let's take out the 2, we have omega over 4 epsilon naught, the integral of u at the power of negative 1/2 du. So let's integrate this. It means that we're going to have a, of course, in front, the usual one of 4 pi epsilon naught. And then we have, what comes out of it is going to be a positive 2. So remember, it's going to be the opposite of 1/2. It's going to be 2. And then u at the power of 1/2. So now let's rewrite it. We have the 2 on top and the 4 here, so let's get rid of it again. And then let's rewrite, instead of u, we rewrite z squared and r squared. So we have omega over 2 epsilon naught times z squared plus r squared under the square root. And then let's put the boundaries in, and we have 0 to r. So we have, of course, omega over 2 epsilon naught And then the first one will be square root of z squared plus r, capital R in this case, squared, minus, and then we have z squared minus 0 squared, so simply z squared, and we have then omega over 2 epsilon naught times, like we did before, z squared plus r squared and the square root minus z. And that is our final answer. Our work time, wow. Nice.